Delaware Tech, Chemistry 100, Chemistry 110, Unit 5 continued, reaction type number 6, oxidation-reduction. Oxidation-reduction reactions, also known as redox reaction, red, reduction, oxidation, involve changes in what we call oxidation state. So let's first talk about what an oxidation state is. Well, if we were talking about ions, or as in ionic compounds, oxidation state is pretty easy. It's just the charge of that atom. So if we had a sodium ion, for instance, that would have a +1 charge, so its oxidation state would be +1. So, and that's true of any of the group 1A elements except for hydrogen. The alkali metals like lithium, sodium, potassium, rubidium, cesium, francium, etc., these all, when they form charges in compounds, they will have a +1 charge. When they're just plain metals, they have no charge at all. Group 2 elements, group 2A, these are the alkaline earths. When they're in compounds, they all form a +2 charge. So those are the oxidation states of each of those when they're in compounds. The group 7A, also known as group 17, those are the halogens. And halogens can have a number of oxidation states, but in general, if they are not a central atom in the structure of a molecule, if they aren't the center of the molecule, if they're one of the outer atoms, the charge on these would be a -1. The oxidation state would be a -1. And while these may not have a formal charge of -1 in molecules, we're going to call what the charge that it would have had, we're going to refer to that as the oxidation state. So oxidation state is the charge, whether it is ionic and true charge, or even if it's in a molecular compound or a covalent compound where there are no true charges. It's a way of counting the electrons. So halogens we're going to assume are -1 unless you're told otherwise. Oxygen will generally be -2. There are some exceptions when it's found in peroxides. Peroxides have 2 oxygens in them acting together. The oxidation state of each oxygen is -1, but I'm not going to give those to you in exams. So if you see oxygen, assume its oxidation state is -2. If you see a halogen that I haven't told you to calculate the charge of, you assume that it's -1. And hydrogen can be +1 or -1 because it can either lose an electron to be +1 or gain an electron to be -1. But in all the examples I'm going to give you, it's typically going to be +1. So if you see a hydrogen, assume it's +1. If you see a halogen that's not a central atom, assume it's -1. If you see an oxygen, assume that it's -2. So these are the rules you're going to go by. Now, you also have to know that when you're determining the oxidation state of all the atoms in a particular compound, you need to know that when you add up all the oxidation states of any element, any elemental form, the oxidation states of every atom is 0. So H2, both of those H's have an oxidation state of 0. F2, Cl2, Br2, all the halogen diatomic elements, they are all composed of atoms that have 0 oxidation state for each of them. Any elemental form of any element, all the atoms will have an oxidation state of 0. So metals like sodium metal, I just told you sodium metal in a compound is +1, but sodium metal by itself, or iron metal, or uranium metal, the metals in the metallic form that look like metals, these are all the elemental forms, and they have a 0 charge on them, and therefore a 0 oxidation state. Gases like argon and neon, these are noble gases. They are usually not found in compounds. Oxidation state is 0. P4, all phosphoruses in P4 have an oxidation state of 0, etc., etc. So if it's a single atom, or it's an atom in the elemental form, the oxidation state is assumed to be 0 unless you see a charge on it. Likewise, all neutral molecules have a total oxidation state. If you added all the oxidation states of all the atoms in a molecule or in a compound, the total will always be 0 unless you're starting with an ionic group, like a polyatomic ion. So all elemental forms, the atoms are all 0, and the total of any compound, any neutral compound, will be 0. And if you use these rules, these 3 sets of rules here, you can determine the oxidation state of all the other atoms in a specific compound. So the sum of the oxidation states of a neutral atom will be, of a neutral compound will always be 0. But the sum of the oxidation states of all the atoms in an ion will be the charge of the whole ion, the whole particle. So we use simple algebra to determine the oxidation state, and I'll show you some examples that'll make it more obvious what this actually is about. So let's determine the oxidation state of sulfur in this ion, HSO4 -1 ion. This is called the hydrogen sulfate ion. It's a polyatomic ion composed of 6 atoms. Well, we know that the sum of all the oxidation states will equal the charge. And this is not a neutral molecule. It has a charge of -1. So that means if we add the oxidation state of the 1 hydrogen plus the oxidation state of the 1 sulfur plus 4 times the oxidation state of each of the oxygens, we will get the total charge on that particle, which in this case is -1. So here I've written it as an algebraic formula. The charge of H plus the charge of S plus 4 times the charge of the oxygen equals -1. Now we also know some things. We can assume that hydrogen is +1. We can assume that oxygen is -2. So the only thing we don't know is the charge of the sulfur. And now it's just a matter of simple algebraic rearrangement. We have 1 plus the charge on the sulfur plus 4 times -2 will give a sum of -1. We can simplify that to 1 plus the charge on the sulfur minus 8 equals -1. So that means the charge of the sulfur -7, because 1 minus 8 is -7, equals -1. We move the -7 to the other side, so we're adding 7 to both sides. We get that the charge on the sulfur is +6. And we have to say the word plus or minus if it is not 0. So it's +6, -3, 0. You have to say whether it's plus or minus unless it's 0. So let's look at some examples of formulas where at least one atom has an unknown oxidation state. In the first example, water, well, water, we know the oxidation states of all the atoms. We know that the oxygen has a oxidation state of -2, and each of the 2 hydrogens are +1, and if we add the +2 and the -2, we get a total of 0, which is what we expect because water is a neutral compound. It's a neutral molecule, therefore the sum of all the oxidation states should be 0. And that works out. So there's nothing really to figure out here. But if we look at the next one, this is nitrate, NO3 with a -1 charge. We know that if we add the oxidation state of the nitrogen plus 3 oxidation states of the oxygens, we should get a total that's equal to the charge of -1. And I won't go through the whole math on this, but what that means is that you must have had an oxidation state of nitrogen of being +5. You would solve for the oxidation state of nitrogen. You'll find it's +5, and I've written that the oxygen is the -2 that you already knew it was. And you see that when you add everything up, you get a total of -1, which is in fact the charge of this polyatomic ion. The next one is potassium permanganate. It's an ionic compound composed of a potassium ion, which you know is +1, and a permanganate polyatomic ion, which has an overall charge of -1, but that's not going to help you right now. You see that this is a whole compound, so if you add the oxidation states of all 6 atoms here, you should get 0. And you know that the oxygen is -2. When you plug it in the formula, you'll find that the manganese is +7. So try that on your own. I'm going to pause here for a second so you can try these, and I'll show you one more example. Okay, I'm going to show you the next one. This is dichromate, another polyatomic ion that has 2 chromiums, 7 oxygens, and an overall charge of -2. So if we were to actually try to solve this, we know that the oxidation state of the of the chromium is unknown, and we have 2 of those, plus 7 oxidation states of oxygen, and we know those are -2s, should give us the total charge, which in this case is -2. That's this number right there. Well, if we know this is -2, and we have 7 of them, well, that's a total of -14. And the total equals -2, so we have 2 times the chromium charge, or in this oxidation state. -14 equals -2. If we add 14 to both sides, this side becomes +12, and this side, the 14s cancel, and we just end up with 2 oxidation states of the chromium equals +12. Therefore, the oxidation state of 1 chromium is +6. And it's important to say the plus if it's a plus and the minus if it's a minus. You must have those terms in there. Okay, I'm going to erase these notes here and show you the answer, and I'll show you the answers for the remaining ones. You can pause right here. Okay, and here they are. And this one, the phosphorus has a oxidation state of +4. In this one, the carbon has an oxidation state also +4. And here, the chlorine, which is not an outer atom. It is the central atom. You know that because there are 4 oxygens around it. You would be told that it's the central atom. It has an oxidation state of +7. So here's a question. What is oxidized and what is reduced in the following reaction, and what are the spectator ions? Well, first we have to know what that means. Oxidation state means, oxidized means that the oxidation state is going up. And we can just say oxidation state is increasing. In other words, the charge is getting more positive. It's getting to be a bigger number. It's oxidizing. It's losing electrons. So this is losing electrons, oxidizing. The charge goes up. The oxidation state goes up. Reduction is just the opposite. You are gaining electrons. So what is being reduced? Well, what is being reduced is the oxidation state is going down. You are going to a more negative number. So for instance, a reduction would be going from +2 to +1, or +2 to 0, or 0 to -3. Those are all reductions. Each time the number went down, sometimes to a negative value, but it doesn't have to be. It just has to get to a smaller number. That's a reduction. Whereas an oxidation is an increasing number. You can go from an oxidation state of 0 to +3. You can go from an oxidation state of +2 to +4. You can go from an oxidation state of -2 to 0. In each of these cases, the number went up. These are all oxidation reactions. These are all reduction reactions. And I'm going to tell you, we're going to show it a little bit more detail in 2 more slides, but every time you have an oxidation reduction where something is losing electrons, there is always going to be a reduction reaction along with it, because something has to gain those electrons that were just lost. So oxidation and reduction always come in pairs. This is why we call them redox reactions, REDOX, reduction, oxidation. And we pronounce this word redox. It's just shorthand for saying oxidation reduction reaction. We just say redox reaction. So I'm going to erase these notes here, and we're going to look at these compounds. We've got cobalt with cyanides and magnesium, and that's magnesium atoms, magnesium metal, neutral magnesium because it's the elemental form of magnesium. And we make a new cobalt compound and a magnesium compound. Well, we know magnesium compounds, magnesium is always going to be +2. So we know in that case, the charge on the magnesium, or the oxidation state more properly, is increasing. It's going from 0 to 2. That's an oxidation reaction. Whereas in this case, if we look at this compound, and by the way, you don't need to look at the coefficients from the balancing. They're not important to determine the oxidation states. We just look at the formula. And we know each cyanide is -1. Well, 6 times minus 1 is minus 6. We have 1 cobalt, so this must be plus 6. And therefore we know the cobalt is plus 6 here, but the cobalt is only plus 3 here. So in this case, the cobalt is going from plus 6 to plus 3. That is a lowering of the oxidation state, a reduction of the oxidation state. That's a reduction reaction. And the cyanides, which are composed of 1 carbon and 1 nitrogen, and you can figure out what the oxidation state of each is. But the fact is, you don't have to bother because we know that cyanide is cyanide here, and we know cyanide is still cyanide here, and we know cyanide is still cyanide here. It never changed. So the oxidation states of the carbon and the nitrogen, as well as the charge of the cyanide, none of those changed during the reaction. So that's what we call a spectator ion. It just went along for the ride. There was no oxidation reduction. And these will happen because you'll frequently, but not always, find spectator ions because they have to be there to balance the charges that are changing. So I'm going to erase this, and I'll just show you here the charges, and cyanide's a spectator ion. Here's another one. 2 leads, don't worry about the 2, plus molecular oxygen, this is the elemental form of oxygen, oxygen gas, produce 2, again don't worry about the 2, lead oxides. Now which lead oxide is this? Well, we know this oxide is minus 2, so the lead must be plus 2. So we know this lead is plus 2. But what about this lead in the beginning? Well, that's the elemental form of lead. It's plain lead, lead metal, 0. And what about the oxygen here? Well, it's elemental oxygen. It's 0. So what we have is a case where for the oxygen, the charge is going from 0 to minus 2. And for the lead, it's going from 0 to plus 2. This is reducing its value, so there's your reduction, and this is increasing, so that's your oxidation, and there is no spectator ion. I'm going to delete this and show you the neatly written version right there, and that's that. So oxidation loses electrons, becomes more positively charged, and reduction gains electrons, becomes more negatively charged. Now, it doesn't mean it becomes negative, it just means it becomes more negative. So let's look at some examples of redox reactions in everyday life. Batteries, for instance. Batteries are a classic source of redox chemistry. In the old electrochemical cells, sorry about that, in the old electrochemical cells, we used to have the oxidation and reduction reactions happen in 2 different reaction vessels. So here we have zinc metal, this strip of metal, that's being slowly converted into zinc plus 2 ions that end up in the water. And that's an oxidation reaction. And over here, we have copper plus 2 ions that are slowly being reduced to copper metal, which actually plates right on top of the already present copper plate in the other side of the battery. These are called electrochemical cells. Nowadays, the batteries are made in a more compact manner with different layers. So you have the zinc layer here, and instead of copper, in this particular battery, it uses manganese plus 4 ions that are reduced to another ion of magnesium, something like manganese plus 2, or maybe even manganese 0. Almost all of metabolism is based on redox chemistry, either breaking down sugars as in respiration, or what plants do, whereas they create sugars from carbon dioxide and water and produce oxygen in the process. So let's look at photosynthesis. You have carbon dioxide, which is the most oxidized form of carbon, CO2, and you're turning it into a somewhat reduced form of carbon in the glucose. Now, you are not responsible for knowing that in a complex reaction like this. I'm just letting you know the oxygen, that the carbon here is being reduced when you're making sugars. The oxygens that are present here and here are all minus 2 because they're in compounds, but the oxygen that's formed in the oxygen gas, it's a elemental form of oxygen, so the oxidation state is 0. So this would be going from -2 to 0. That's an oxidation state. The number is increasing. The oxidation state is increasing. And in respiration, the processes are reversed. And we have a lot of other reactions. Rusting is oxidation of iron metal with 0 charge to iron oxide, which might have a +3 charge on it. Electroplating is very similar to batteries. It's done in a different way. Instead of letting the reactions go on their own, you use electricity to drive the reaction backwards, but it's essentially making this reaction go the opposite direction as in a typical battery. And food spoilage, well, food spoilage is just bacteria and other microorganisms doing respiration of the sugars in food and the other molecules in food, breaking it down. So that's essentially their version of respiration. So all of these are oxidation reactions that you encounter every day. So let's talk about oxidation reactions or redox reactions. So these are reactions where the charges on the atoms, more correctly the oxidation states on the atoms, are changing because electrons are moving. Some atoms are losing them, that's oxidation. Some atoms are gaining them, that's reduction. So one atom will become more positive, that's the one that was oxidized, and one's becoming more negative, that's the one being reduced. So this is a very simplistic way to write an oxidation reduction reaction. I don't expect you to write it this way because it is kind of an awkward way to write it and think about it. But you have one atom with a charge and you have another atom with a charge, and one atom is increasing its charge. So A is losing electrons to get more positively charged. That's an oxidation. Whereas B is gaining electrons, so its charge is going down. That's a reduction. And that gets confusing writing this, so I'm not going to write it in this form, but you should be able to recognize the charges on atoms. So here's kind of a pictorial way of looking at it. These are two young ladies, and think of them as two atoms. One has a lot of electrons and the other has no extra electrons, and one passes them on to the other. So A lost her electrons, that's an oxidation. B gained her electrons, that's a reduction. So A is now more positively charged, you can think of it that way, and B is more negatively charged. So oxidation and reduction always happen in pairs. They have to, because one atom's losing electrons, they have to go somewhere so another atom picks them up. So oxidation is loss of electrons. Oxidation is loss. Remember that phrase. They become more positive. So again, that would be going from 0 to +2, or maybe +2 to +3, or maybe going from -2 to 0. All of those are becoming larger numbers, more positive numbers. Those are all oxidation changes in oxidation state. Reduction is gain of electrons. So now we're talking about electrons. We're not talking about oxidation states. The reduction gains electrons. It becomes more negative. B is being reduced in this case. So oxidation is loss. Reduction is gain. Oil rig. That's the way to remember it. Oxidation is lost, oil. Reduction is gain, rig. So here's another example like the one I showed you before. Now it's iron 3 nitrate and zinc metal make iron 2 nitrate and zinc nitrate. So that's an iron 3 becomes an iron 2. That's a reduction. And the zinc 0 is becoming oxidized to zinc +2. So we have an oxidation reduction reaction. I'm going to delete that and show you there. So iron +3 is accepting electrons, it's being reduced. The zinc is losing electrons, it's donating them, so it's being oxidized. And you'll notice the nitrate is not changing. It's still nitrate before and after, so nitrate is the spectator ion. The oxidation states of the nitrogen and the oxygen and nitrate didn't change at all. So here are some examples of all 6 reaction types, and I'm going to tell you right now, the first 5 reaction types, some of them are also oxidation-reduction reactions. So when we're looking for a reaction type, we want to go with the main type. If there's no other type that it fits, then look for an oxidation reduction, and you can call it that. So the first one, remember our clues. If you're adding 2 things together, and here you really need to know it's a combination, you can figure out what the product is. Well, if we're combining PCl3 and Cl2, well, we simply get PCl5. And to balance it, there's nothing to do. It's a 1 plus 1. It gives you 1. So it's already balanced. Let's look at water. We're starting with water, and something's going to happen. That immediately tells you have 1 reactant, so you know right away it must be a decomposition. And if it only has 2 different elements in it, hydrogen and oxygen, it's probably going to split into its 2 elemental forms, hydrogen gas and oxygen gas, H2 and O2. And now we balance it, and there we go. Zinc plus HCl. So we have an element and a compound. Remember our clues here. Element and compound is a single replacement, and you form a new compound and a new element. So the zinc and the hydrogen are swapping places. Just one pair of things swap places. That's why it's called a single replacement. But when you get the H, it must be in its elemental form, H2. Just like you saw before when you split off the H's from the water and the O's from water, they have to end up in a stable form, which in this case are the elemental forms. Iron oxide, iron 3 oxide, Fe2O3. Well, that's another decomp. You see there's only one starting material. I'm sorry, I forgot to balance that one. So you break it down into iron and oxygen gas. The elemental form of iron is just iron metal, neutral iron metal, and oxygen gas. Balancing it, we get these numbers. So go ahead, go through these, practice them, and see if you can determine the reaction type for the remainder, as well as the products, and then balance the reaction. Now, if you get the wrong products, your balancing is never going to be correct. So you want to be sure that when you make your products, you essentially balance the formula of each compound first, and then balance the whole chemical reaction. For example, I'll skip along here. Let's look at number 6. We have copper bromide, copper 2 bromide, forming sodium carbonate. That's a compound and a compound. That tells us it's probably a double replacement. The copper and the sodium swap places. Typically, metals and hydrogen will swap with each other. If there are only 2 metals, they swap. If there's a hydrogen there, that will swap. And then anions will swap with anions. So we have bromide and carbonate swapping. So that's a double replacement. So we'll end up with sodium with the bromide and copper with the carbonate. But remember, the carbonate is a -2. And the copper, you already know, is a +2. And that doesn't change. In a double replacement, they don't change charges. So it's got to be crisscross simplified, so they just end up being 1 and 1 instead of 2 and 2. And sodium and bromide, also 1 and 1. So those are the formulas, and I'm going to clear that. And then when you balance it, you have to be careful, but there's only one number to change, so you've got that. And so go ahead, go through these. With this number 7 here, you've got OH, 2 OHs on this, and you've got 2 H2s on this. So you're going to end up forming water from each of those. But the fact is, this tells you you must have 2 waters being formed. And the remaining magnesium ion and sulfite ion find each other and become magnesium sulfite. So please be careful when you're forming the compounds as well as when you're balancing the reaction. I'll pause here for a second and then show you all the answers. Okay, and here are the remaining answers. And before I finish, I just want to point out number 10. Number 10 is a compound and an element, but I'm telling you what the products are in this case, that they are 2 compounds. So this is neither a single replacement nor a double replacement, but the cobalt is plus 6 here. The cobalt is plus 3 here. Oops, sorry. Hard to write that. The zinc is 0 here, and the zinc is plus 2 here. So the zinc is getting oxidized, and the cobalt is getting reduced. And in this case, I would give you the products, and I would give you one of the numbers so that you could balance it properly, because you really haven't learned all the skills to balancing a redox-only reaction by itself. There's some things that are beyond the scope of Chem 100 and Chem 110. So go ahead, try these, and make sure that you're able to categorize them, write the right products once you know the category. So sometimes you need to know the category first, and then be able to balance these equations. And with this, we'll stop here.